Alright, so this is video number 2 for section 2 of chapter 8. We already went over synthesis and decomposition. Now we just need to do single displacement, double displacement, and our combustion reactions. So, flip all the way to single displacement here. Right? This first reaction, I have one element replacing a similar element in a compound. Right? I have this general equation here that says A is going to replace B in this compound. Right? A and B are similar to each other. Since B comes first in the compound, BX, I can assume that A and B are metals, because metals always come first. Right? You always put that positive charge first in a formula like that. So A is going to replace B, so you end up with AX instead of BX, and a B that's all by itself. Right? When you're looking at an equation, when you're looking at a formula equation, and you want to identify it as being single displacement, what you're looking for is a lone element, which to me is easy to remember, right? Single, it's all by itself, right? Whereas that lone element is going to react with a compound. So B is not all by itself, it's with X already. But A is going to replace B in that compound, then B is going to be all by itself on the other side of the equation. So know what to look for, know how this is going to look. That's just a generic equation there, but it does help when you're trying to do this to look back to that here and there. So our displacement, right, of a metal in a compound by another metal would look something like this. I have aluminum, right? That's going to replace a metal in my compound here. My compound is lead nitrate. It's a plumbous nitrate. It's lead 2 nitrate, right? So that is important that you understand what charges are going on, right? So you can balance things appropriately, right? But if I have this reaction here, lead's my metal, right? Aluminum's going to displace that lead, right? So I'll have an aluminum nitrate as a product instead of a lead nitrate. And aluminum has a different charge as an ion, so I have 3 nitrates to go with that aluminum instead of 2 with the lead. But then I displace the lead. The lead is going to be singular all by itself as the other product in this reaction. So again, modeling and then balancing. I do have to make sure that once I get these products, these are correct products, that I can balance the whole equation. So that's the next part. Obviously, since I have a 2 and a 3 thing going on here, I probably need to stick with that for my least common multiple of 6. But then I'm going to need 2 of these aluminums over here, and I'm going to produce 3 of those lead atoms over there. But this should be balanced now. The only other thing that might be included again would be the states, right? Sometimes the states are important, sometimes they're not, right? That aluminum would have been solid. This lead nitrate was aqueous, meaning it was dissolved in water. But then on the other side, I have an aqueous aluminum nitrate, and then that lead is going to come out as a solid. Now, that's a situation where, again, I might use that down arrow instead of saying that it's a solid, because I'm going to see that precipitate, right? Aluminum and lead aren't real different from each other, right? They're both silvery, obviously, but that lead is a little duller and a little darker gray. You can tell the difference between the solid you started with and the solid you ended up with. So you would know that a reaction took place here. You can see it happening, right? But again, modeling, doing what you need to do, right? When we did this on the homework quiz before, it was an aluminum replacing a copper, which it's real easy to tell the difference between aluminum and copper, right? So when you started out with an aluminum, a silvery metal, and you ended up with that copper-colored metal, right, that would be a really obvious reaction. But One thing displaces another. That's all you got to worry about. Next type of reaction, I can displace hydrogen in water, but with a metal. Now, if this is the case, you actually have two possible outcomes. And we'll talk more about this in the next section. But if I have a very active metal like a sodium, and I react it with water, again, the first thing in that compound in the water, in that H2O, is the hydrogen. Hydrogen is more like a metal than the oxygen is, right? Oxygen is definitely a non-metal. Hydrogen can act like a metal sometimes. So sodium is going to replace that hydrogen. But it depends on what type of metal you have, what products you're going to get. So again, this one right now might be more important for you to be able to identify that it's a single displacement as opposed to knowing which product you're going to get. But in the next section, in section 3, you'll definitely know which product you're getting. That sodium is going to react with water in this first one to make a sodium hydroxide. And hydrogen gas. Right? So a couple detail things that we should look at here, because we're going to need to know these next section at least, right, is that this water here, the state's going to be a liquid, right? And I'm going to make these products over here, again, in liquid water. When I make hydrogen gas, I'm going to see bubbles. It's going to be pretty obvious that this reaction is occurring. It's a really vigorous reaction. It's going to release a lot of heat, actually. And if you Google this, if you just searched on YouTube, sodium reacting with water, it's an explosively reactant. It's an explosively energetic reaction. So I'm going to make this sodium hydroxide. I could tell that that sodium hydroxide is there. It's aqueous because it is a base. I could use an indicator to show that my new solution is basic, right? But again, the most obvious thing is going to be the bubbles that occur from the get-go. But hydrogen gas is also flammable, so all that energy being released, the reason this is explosive is because that hydrogen lights on fire because there's so much energy released in this reaction. So again, sodium and water makes sodium hydroxide and hydrogen gas. Whereas if I had aluminum reacting with water, it can still displace hydrogen, but it does it differently. So again, same two reactants, but I'm going to get different products, right? Aluminum is actually going to displace both hydrogens in that water. So I just have aluminum and oxide left, right? And I have to balance that appropriately with a 2 and a 3. And then I'm going to have my hydrogen gas. Again, I'm going to know that this reaction occurs, but there's also different conditions that are going on here, right? That water, in this case, is going to need to be a gas to begin with. It's going to have to be really, really hot. I need steam to react with aluminum metal to make these products. So you're going to see a difference if there's liquid or a gas. If that water is cold or if it's hot, that is going to make a difference. I am going to require some conditions here. It has to be greater than or equal to 100 degrees Celsius in order for me to make that reaction work. But again, usually this reaction is occurring when you're boiling water in a tea kettle, right? So it's definitely possible that it's going to happen. It's just only going to happen in those conditions. If you had water just sitting in that aluminum tea kettle, right, this reaction will not occur because the water is too cold for it to occur. Otherwise, once it's boiling, once you have steam in there, then you're going to see a little bit of this reaction happening. So again, I am going to make a hydrogen gas, but I'm not going to necessarily see it bubbling because the water was already so hot it was bubbling anyway. I can't tell the difference between the boiling and the bubbles from the hydrogen gas. Otherwise, I am going to make this solid byproduct, which in this case may or may not be a precipitate. Again, in the boiling water, you might see some of that forming on the sides of the container, that aluminum oxide. But again, definitely a difference between one reaction and the other. So you get two different possible outcomes, but it depends on the conditions. It depends on what kind of metal you have and how active it is. We'll talk about that next section. But it also right? The water is different in both cases. In order for it to work for aluminum, since it's less active, that water has to be really, really hot. You need that extra energy to make it work. So, two similar reactions, but be able to tell that there's single displacement in either case, right? I still have sodium replacing hydrogen, just not all the hydrogen, because it leaves one in the hydroxide. Aluminum's replacing hydrogen, though, to create that hydrogen gas, right? That's displacing it altogether, right? But you still see a single lone element in both of these things, the sodium and the aluminum to start, reacting with a compound, with water specifically, right? This is single displacement. Balancing, it should take care of that actually. You should understand that, okay, if I'm going to take one hydrogen out of water, that's going to leave me with one hydroxide, but I'd only have one hydrogen, not two. So I do actually need to have two of these sodium hydroxides and two waters and two sodiums to make this one work. Right? That's going to make everything balanced when it's all said and done. Excuse me. Yeah, that's correct. So now I have 4 hydrogens on both sides, 2 oxygens on both sides, and 2 sodiums. Whereas the other one, again, I'd be looking at my compound over here first. I'm definitely going to need 2 aluminums, and it's going to take 3 waters to make the 3 oxygens I need. So that's going to give me 6 hydrogens. So I need 3 of these hydrogen molecules over here, diatomic hydrogens. So they balance a little bit differently too, but as long as you have good examples, we can model off those later. But they are actually 2 distinct types of reactions. Next is displacement of hydrogen in an acid. Same idea. Hydrogen's like a metal, so if I had an acid here, not water, hydrochloric acid, right? Same thing can happen. A replaces B. Zinc replaces that hydrogen, not the chlorine. So I end up with a zinc chloride instead of a hydrogen chloride. I am going to need 2 chloride ions to go with that zinc ion, because zinc is a +2 charge. And then I'm going to make hydrogen gas again. Hydrogen is always diatomic, so I have to write it that way. And again, balancing, that means I'm going to need 2 of these hydrochloric acid molecules to react in this equation. But again, same idea. I'm making that hydrogen gas. State-wise, I usually put a solid mossy zinc into hydrochloric acid that's aqueous. It's in water already. So I'm definitely going to see bubbles this time again, right? And this product, the zinc chloride, is aqueous. I use this reaction all the time in class to create hydrogen gas because I don't have sodium available to do it. I don't want to boil water to do it with aluminum. So this reaction works in cold conditions again because it's a different reaction. This is not water that I'm displacing hydrogen in. So zinc will do this. I can make that hydrogen gas in class and I use it to make water rockets all the time. Right? It's actually kind of fun to do. Too bad you're not in class. I could make those for you. But maybe next year, who knows. Next one, next reaction, displacement of halogens. This one is different, right, than what we've been talking about. Now I'm going to be dealing with element Y, but it's not going to replace B, it's going to replace X because it's more like X. Halogens are nonmetals, not metals, right? So there's another thing that comes into play too. Halogens, like hydrogen, like oxygen, are diatomic normally. So even though it's singular Y, there's only that Y element in my first reactant there. It's still all by itself, right? There's 2 of them, but it's still a single element, right? So this is still a single displacement. But this time, X is replaced, not B. So my new product is going to be a BY, not a BX. And X is going to come out, but X is also a halogen, so it should be diatomic as well, right? So that's just generic. Let's put in a few real examples, right? What if I had chlorine? Excuse me, I forgot my L. So chlorine, which would probably be a gas. at room temperature, replacing something in this potassium bromide. Again, chlorine is more like the bromine than it is like the potassium. That's why it's going to displace the bromine. Okay? So potassium bromide is aqueous in this solution probably. So chlorine is going to replace the bromine. That means I end up with a potassium chloride instead of a potassium bromide. But bromine and chlorine are similar elements. They end up with the same charge as ions, so you get the same look on both sides. There's one potassium, one bromine. There's one potassium, one chlorine. Those are correct formulas. This also would probably be aqueous in that solution. But then bromine would be removed, and again, bromine diatomic all by itself. So I can't write it singular there. Bromine actually is a liquid at room temperature, so it'll probably stay in that solution instead of bubbling out. But you could test for it in other ways. Otherwise, this reaction is almost complete. I just have to balance it. Because of those diatomic natures of chlorine and bromine, I'm going to need a 2 here and a 2 here to get that to balance. Again, kind of depends. But sometimes I'm going to put 2's here. Sometimes I'm going to do it a little bit differently, because this could have a slightly different look. Another example, just so we can see, right? Maybe I have fluorine, again, a gas. That's going to replace chlorine in a different compound. So I have magnesium chloride as aqueous. Notice that magnesium chloride, forgot my G, there's actually 2 chlorides per magnesium because magnesium has a +2 charge, right? So replacing chlorine with fluorine here, I get a magnesium fluoride. Again, I'd also need 2 fluoride ions to go with the magnesium, so that didn't change. One side or the other, it's going to be similar. Plus, again, I replaced the chlorine. Chlorine is a gas at room temperature, so I could write that as a gas. And actually, in this case, let me fix that. I might use that up arrow because I'm definitely going to see bubbles now since it was in solution that this is occurring. But fluorine replaced that chlorine, and notice that this is already balanced now, right? If you have a group 2 metal, right, it's already going to be balanced because of this 2 here and this 2 here, right? Which is different than when I put a 2 here, because I had to have 2 bromines because there were 2 bromines over here, right? So notice that you're definitely going to have 2's, but they might be in different places. So you're either going to have the 2 pink 2's in your generic equation, or you're going to have the 2 purple ones, right? But either way, you're going to have to get this balanced overall. And it could actually look different, because if you had an aluminum as your metal, then you'd actually have a 3 where that purple 2 is, and then everything else would change too. So, but generally speaking, you're going to have one of these things or the other, and it kind of balances itself that way, right? Just be consistent on both sides. But otherwise, those are 2 examples. There could be many.